Hello statistics students, my name is Jami Emigh, and this video starts our discussion on chapter 10. Title is Correlation and Regression. A correlation exists between two variables when the values in one of the variables are associated with the values in the other in some way. A linear correlation exists when the correlation results in a pattern that can be approximated by a line, and we call that line the regression line. This lowercase Greek letter rho, we're going to use it to represent the linear correlation coefficient for a population of paired data. And we're going to use lowercase r for the linear correlation coefficient for a sample of paired data. R is always going to be between -1 and +1 inclusive. And the closer it is, the closer R is to -1 or +1, the stronger the correlation between the two variables will be. For example, if R is 0.851, then we can see the relationship on this scatter plot. Wherever we go on X, we're going to go up on Y, over on X goes a little higher on Y, a little further over on X goes a little bit higher on Y. So each one of these dots in the scatter plot represents two things. It has an X coordinate and it also has a Y coordinate. So it appears that as the X coordinate increases, the Y value is also increasing, and we could probably capture the behavior with this line like this. So we would say that this has a positive linear, for the line there, correlation. Here's an example. This one's even stronger. You see how this one line would capture the behavior even more so than the last one? That just means that it is a stronger correlation. But since it's going downhill, negative slope, that means as we increase the X value, the Y value is actually decreasing, okay? So we call that a negative correlation. And look how strong this one is. R is equal to -0.965. Remember, the closer that this value right here is to 1 or -1, the stronger the correlation will be. And that is that this line can capture the behavior of the data values. Here's a good example. Check out this scatter plot. It appears there's no line that we could draw that would capture any prediction about if X is over here, then Y is going to do this. It's all just scattered. We would call this a good example of there's no correlation. And for no correlation, that's when R equals 0. So maybe visualizing this on a number line, this inequality might be helpful. If we're here at -1, that's the smallest possible number R could be. And then once we hit 0, we're at the weakest correlation. We call that no correlation. And then when we get back to 1, that's the max it could be, we're back at a strong correlation. So strongest correlations would be -1 and the +1. The weakest correlation, or we would call no correlation, would be at 0. And then, of course, there's everything in between. For example, here, our 0.851, that was here, approximately. Our -0.965 was approximately here. So you can see the closer it gets to 1 or -1, the stronger the correlation. Hovering around 0, no correlation. All right, D is a nice example because there is a pattern. Looks like a parabola. You guys remember graphing those? This parabola, this quadratic formula, you might remember, taken to the second power. There's a pattern there. It's just that it's not linear. So there's no line that would capture this. So it still has a relationship. It's just a non-linear relationship. And that's fine. Variables can do that. They can have a pattern in some way that doesn't have a best fit line or a regression line. A regression equation is the equation of you'll often hear it called the best fit line. So if we could find the equation of these purple lines right here that we sketched, that would be the regression equation for what we call best fit line. That equation expresses the relationship between x, which we call the explanatory, or we call it the predictor, or sometimes you'll hear it as the independent variable, whereas y hat, that will be the response or the dependent variable. We'll work with that a little bit more, but you guys have probably seen it. Well, I know you have in the equation of the line y equals mx plus b. Same thing. B is the y-intercept. M is the slope, so it could be positive or negative. And then x and y are those two variables that we're checking if there's a correlation between the two or not. So x would be our independent variable, and then y hat would depend on whatever we input for x. When we're asked to predict the value of y based on x, okay, this is going to happen a lot, you guys, right here. That's what a lot of the use of stats is, to make predictions. So one particular way to make a prediction is to check one of these two options. Okay, here we go. This option, if p is low, and you guys know what that means. That means if the p-value is lower than the significance level, then we're going to conclude that yes, there's a correlation between the two variables. And if that's the case, we're going to use that regression equation, the y hat equals a plus bx, to make our prediction. This might look backwards to you, and we switched the b right here from the m to a b. This, you guys, don't let this confuse you. This is the same way to write the equation of a line. It's just that this right here is m if you're talking y equals mx plus b. This right here is the y-intercept, or b, right here. So these two, I know they look different right now, but they're the same. Y-intercept, slope, x is the independent variable, y hat would be what we predict dependent on x. Now there's another case. If p is high, and you know what that means. That means that the p-value is higher than the significance level. Then we're going to conclude that there is no correlation between the two variables. And if there's no correlation between the two variables, like this one, you guys, this one right here, this would go with this case, the second one listed. Boom. Okay. If there's no correlation, we're going to get a high p-value. So we're going to conclude no correlation. And then we're going to use the average of the y values as our prediction. Okay. There's no equation of a best fit line here. So we wouldn't want to plug x into an equation and use that to output some predicted y value. So instead, if there's no correlation, we, right here, use the average of the y values as our prediction. So as a statistician, if you're ever asked this word right here, predict, then you have two things to choose from to make your prediction. Either plug x into the equation, whatever it outputs, or the average of the y values. Use the equation if there's a correlation between the two variables. Use the average if there's not. All right. Use the paired data below to find the value of the correlation coefficient R. Is there a linear correlation between shoe print length and heights of males? And we're going to use, as requested, alpha equals 0.05. Okay, so we take this data right here, shoe prints and heights. So this right here, this is one person. but we measure two things from them. We've got their shoe print length and their height. Here's a second person, a third. These are for males, fourth male, and we have a fifth person there. So of these 5, if we sketch them into a scatter plot like we see here, okay, each one of these is one of those people, one of those males, and it has 2 values. It has a shoe print length as well as their height. Okay, if we're just looking at these 5 on the scatter plot, it looks like maybe there's a linear correlation. Okay, as the shoe print length increases, it looks like the height might be increasing as well. Not necessarily here, but this might be a best fit line. It's at least worth moving forward with the question. If you sketch your scatter plot and they're all over the place, no need to even move forward. But ours looks pretty reasonable. Our requirements are met. That's the data are a simple random sample of quantitative data, check. The points appear to be roughly approximated by a straight line pattern, check. And the third requirement is that there are no outliers, check. That being said, we can set up our null and alternative hypothesis. Sub not and sub, you'll see a 1 or an A, just 2 different standard notations for that. Set it up as rho equals 0 and where rho does not equal 0. Null hypothesis is always equal to, and so we're testing the claim, alternative hypothesis, that there is a linear correlation, okay? We're going to use a program in StatCrunch called the regression program. All right, let's see how to do that now. Okay, once in StatCrunch, we go to Stat, and the regression program is here. We're going to look at the simple linear. Tell the program where your x variables are. So they opened up in column 1 for us. Your y variables, those opened up in column 2. Don't worry about any of this, you guys. Skip it, skip it, skip it, and hit compute. Okay, now we do have to spend some time reading this output screen, right? Lots of details here. We need to know how to read them. All right, first thing I want you guys to practice doing on the output screen is way down here at the bottom. Click on this arrow, turns to page 2, and it shows us a scatter plot of that data. We had a little snapshot of it already in our notes, but if there isn't a little snapshot of it already, you can hit this arrow right here to see the graph of that scatter plot. Okay, let's go back to page 1 by hitting this arrow here. All right, starting from the top, there is something they're going to ask us from right here. If they ask us what the correlation coefficient is, it's listed here with a capital R. So heads up for that. So that's our correlation coefficient, 0.59. Okay, they're also going to be requesting from us 2 things from this row. Okay, make sure you go to this row here. It's in the table under parameter estimates, and it's in the row that starts with the slope, okay? They're going to be asking us for, right here, the test statistic, so 1.2698528, and the p-value, 0.2936, which is what we will use to make our predictions. Okay, so heads up for all of those things on this output screen. This is lowercase r, correlation coefficient, and here we have test stat, p-value, and here we have the graph. All right, let's write that up in our notes. Okay, the p-value was 0.954, which is higher than the significance level of 0.05. So we would say that p is high, the null will fly. So we're going to fail to reject the null hypothesis, and then we'll state our conclusion that there is not sufficient evidence to support a linear correlation between shoe print lengths and the heights of people. And here we have a nice visual on what we just did. Two tails, see, -1 over here. Then there's a correlation region. All the stuff closer to 0 would be no correlation. Then when we pass some bar, we get a strong correlation again. Our sample data had R was equal to 0.591. Okay, that was the test stat. It was on the output screen of StatCrunch. The critical value, here's something we need to note, you guys. This critical value right here, if you're not, well, we used the p-value method, okay? We compared the p-value to the significance level, and that was enough. However, if the question asks you, well, what is the critical value? You can't get it from statistics, or sorry, you can't get it from StatCrunch. You'll have to get your these critical values, get CVs from, and there'll be a link right there in the question from link. I'll show it to you. I'll show you one. Okay, so if you're working on a question and it asks you for the critical value, there will be a link there. You click on it and I'll show you how to read it. We'll do it for this one here. Things we're going to note to read the critical value will be what our sample size was. We had 5. I know it might look like 10, but it's not, okay? Sample size is 5, which means that our degree of freedom is 4, and our significance level here. So we'll need that information to read the critical value. Let me show you. Okay, look at this example. This is chapter 10 homework question. And you see we've got X values, Y values. So you can open these in StatCrunch right here. StatCrunch will give you the graph. Remember, you have to hit the little arrow on the bottom of the output screen. It'll give you the correlation coefficient R. It'll give you the test statistic. It'll give you the p-value, but it won't give you the critical value. But if you go here, it says click here to view a table of the critical values. You'll click on that, and it's a real straightforward table. You basically choose between alpha equals 0.05 and 0.01. So this was ours right here. So we're in this column, and you go to the row of your sample size, which is 5. So at the intersection of a sample size of 5 and alpha 0.05, right there, that intersection is the critical value 0.878. So should you need it, if they ask you for it, their link will be right there. All right, let's continue with this example. We're asked to predict the height of a person with a shoe print of 29 centimeters. All right, you guys, in the last slide, we determined right at the end, well, that looks weird, right at the end here, we said, based on these 5 samples, there is no sufficient evidence to support a linear correlation between shoe print length and heights of people. Okay, think about that. Based on this sample of 5, we say there is not sufficient evidence to support a linear correlation. Okay, if that's what we're saying, if we're saying there is no linear correlation between shoe print lengths and heights, then when the task is this right here, predict the height, we should not be using any equation, because we said there is no linear correlation, no strong one enough for an equation. So, well, what do we do in that case? Well, since P is high, we do not support a linear correlation, and the regression equation is what we call, it's not a good model, okay? Not a good model means don't use it for your predictions. What we do instead is use the average of the Y values to make our prediction. Okay, we can do that. Our Y values were 175.3, 177.8, 178.4, 175.3, and 172.7. Add them all up, divide by the number of items you add up, And our prediction of a person's height with shoe print length 29 centimeters is just the average height, because we're claiming it doesn't have any correlation with the shoe print length. Okay, but let's say we are like, no, I really think there is a correlation between shoe print length and height. Maybe we should sample more. What if later we go and look at 40 more pairs of data that we gather? So 40 more males, we measure their shoe print length and their height. With the addition of all that data, it ends up changing on us from high to low. What happens when the p-value is high? We say no linear correlation. But if it changes from high to now it's low, we say that there is evidence to support linear correlation. And that means that the regression equation, the equation of the line, the equation of the best fit line, is what we call a good model. And we use good models to make predictions. So we would use y equals a plus bx for our prediction. Now, we didn't look carefully at it. We didn't pay attention to it. But if you go back to, I closed mine already, but if you still have your StatCrunch output screen open, you'll see this equation. It's above the two tables. It's on the output screen, but it's above the two tables. So you'll find the 80.9, the plus, the 3.22, and the x. Remember, y is the dependent variable, x is the independent. This right here would be the slope, 3.22, and this would be considered the y-intercept for that line. Now, to use that equation to make a prediction, we need to substitute in a shoe print length of 29 centimeters for x, and what it outputs is 174.3 centimeters for y. So we would say that the best predicted height is 174.3 centimeters based on more data. Okay, I want you to really pay attention to the top of this slide versus the bottom of this slide. The task was the same, predict the height of someone. Up here, we predicted it using the average of height, and here we predicted it using the equation. How do you know which one to use? If P is high, you use the average height. If P is low, you use the equation. Interpreting R squared, that's the explained variation. R squared is the amount of variation in y explained by the linear relationship between x and y. Example, for the shoe and height example where R was equal to 0.591, if we squared that, we'd get R squared equals, and 0.591 squared is approximately 0.349, so on and so on. And what we say about that value is stated like this. We conclude that about 34.9% of the variation in height can be explained by the linear relationship between lengths of shoe prints and the heights. Some common errors involving correlation, important to note. The first one is called causation. It is wrong to conclude that correlation implies causation or causality. Okay? Just because we as statisticians find a correlation between the numbers, when you take it back to the content experts, that would be their job to address if the change in one variable causes the other variable to change. Okay? So ultimately, statisticians, we get to use the word correlation. We believe there's a correlation between how many nicotine cigarettes you smoke and your blood pressure. We get to use the word correlation, but only a doctor or someone an expert in the medical field gets to use the word causation. So the number of cigarettes you smoke could cause an effect on your blood pressure, for example. Averages. Averages suppress individual variations and may inflate the correlation coefficient. So don't use correlation between averages. And last one, common error, linearity. There may be a relationship between x and y, but it just may not be a linear correlation. Like we saw a parabola, that had a correlation. There was a pattern. It just wasn't a line, so no linear correlation. Marginal change, that's the amount that a variable changes when the other variable changes by exactly 1 unit. I always think marginal change, I need that denominator to be 1. For example, our regression equation was y hat equals 80.9 plus 3.22x. So if we look at the slope of that, 3.22, think of it as over 1. Because we know slope is like rise over run, or the change in y over the change in x. So this means that if we increase the shoe print length by exactly 1 centimeter, then the person's height, predicted height, would increase by 3.22 centimeters. We call that the marginal change. Influential points. For example, is the addition of, let's say we threw in there a shoe print length of 35 centimeters and a height of 25 centimeters. Okay, think about that for a second. Shoe print length, 35 centimeters, height, 25 centimeters. So we're asked, is that an influential point? Well, one way to find out is look at that scatter plot. This was the scatter plot for the shoe print lengths with that additional 40 data values. And this one right here, look what happens from here to here. Adding that influential point, that new shoe print length of 35 centimeters, person at a height of 25 centimeters, look what it did to the best fit line. The line changes dramatically. So we say yes, because the regression line changed considerably. That is what makes that particular point considered an influential point. All right, that's it for chapter 10. So we'll stop now, take a break, and I'll see you next time for chapter 11. My name is Jami Emigh. Thank you for being here. See you soon.